all pairs of vertices. And so the output itself is like n squared, right? Because you have one entry for every pair. It's useful to think of the input as the adjacency matrix because that's going to make lots of the algorithms more convenient. So the obvious thing you would do is you would just run single source shortest paths from all vertices, right? So you just take everyone as the source, and then you go ahead and compute everything. So if you have general weights, you would end up doing n Bellman-Fords, that's mn squared. If it's non-negative, you could do n runs of Dijkstra, and you'd get mn log n, right? And so what is nice is that there's this method of Floyd-Warshall, it's related to matrix multiplication and dynamic programming. And you get n cubed time. So the way to think about this is that when m is like n squared, when it's dense, it's much better than doing either of these methods. And it works for general weights. Okay? So I'll tell you how the Floyd-Warshall algorithm works. And it's a nice exercise of dynamic programming, but it's a very clever dynamic program. So let's start with a really basic dynamic programming algorithm. So I use a dk uv to denote the shortest path from u to v that uses at most k edges. Right? And if it uses, suppose there is no path from u to v less than k edges, I can just set it to be, infinity. Okay? So and one way to think about this to make it convenient is that if uv is not an edge, I'll just set the weight to be infinity. Okay? So it's like infinite weight. So what is d1? d1 is just the weight. Right? And obviously, if there are two vertices without an edge between them, that weight will be infinity, so d1 is infinity. Does that make sense? Right? And d2 would be the shortest paths that involve only two edges. d3 is like at most two edges, at most three edges, so on and so forth. And if you say at most n minus 1 edges, that's the true shortest path. Right? Because there's, no path is going to need more than n minus 1 edges. Because you're just going to, worst case, go through all the other vertices. And that gives you n minus 1 edges. Okay? So far so good? Okay. So what is dk of uv? Well, you can either think of it from the source or the destination is the way to have a path of length k is to have a length of path k minus 1 and then one edge. And so I could write dk uv as saying, well, there's going to be some intermediate vertex x. So this is x over here. Such that there's a path from u to x and then there's the edge uv. And I just minimize over all the neighbors. Right? So I'm just minimizing over all vertices. I'm thinking of this as an adjacency matrix. Right? So that this, instead of doing it over all the in neighbors, I'll just say I'm just maximizing over it. I'm minimizing over everything. Does this make sense? So dk minus 1 of ux plus the weight of that last edge, and I minimize over all the x's. Yeah? So this is the distance from u to v that involves only k edges. Yeah?
As long as x, v is an edge.
Well, if it's not an edge, this would be infinite, and then it would just not be a minimizer. Right? So in the implementation, you could be more careful, but for the sake of the description, this is good enough. Right? Fair enough? Okay. And so the basic recurrence ideas is to build dynamic programming tables based on this. And then what Floyd-Warshall does is actually not do this, but actually sort of implements this in a very clever way. Okay. So what is your dynamic programming table going to look like? If you look at this, you're like, there are obviously three parameters. There's u, v, and there's k. And so I could set up this table d u v k, which is the min over all x, just following this recurrence over here of d u x k minus 1 plus the weight. And of course, I should probably also write this down, is that duv1 is equal to just the weight of uv, and that's your base case here. Right, so this gives us the recurrence that we need. Right, and at this point, this table has n cube entries, right? N choices for u, n choices for k, v, n choices for k. And every entry is going to take O of n time to update theta of n because you have to do this minimization over all of these. And the ordering is also pretty obvious. You start from k is equal to 1, then you go to k is equal to 2, and k is equal to 3, so on and so forth. And so what you have is this, you have this n to the 4 time algorithm. Okay? So it's pretty straightforward. Any questions about this? And so the game now is to how do you get that n to the 4th down to n cube for all pair shortest paths. Okay? So the first thing to observe is you can actually get one of these n's to be a log n instead by what's called a doubling trick. So here, the problem, the reason that we need, and another thing just to be, just to think about the implementation, is if you only care about the last output, you don't have to store all these intermediate values. Like if you have duv for k, then you compute duv of k plus 1, and then you just throw away the k. Right? So you actually need, you can implement basically with theta n square space. Because often storage can be expensive, so all you need is just theta n square space. Okay? Do you see that? Like you don't have to store so you can think of it just like different copies, and you just keep updating k. Okay. So now the next trick is to use a different recurrence. Okay, so there's another thing that I'm going to say here, which, maybe this was the point of confusion last time. So I'll come back to the statement in a bit. What is dn of uv? So if I follow this recurrence here, dn of uv, I'd say that this is the min of x and v of dn minus 1 ux plus w xv. Right? But this is already the shortest path distance, right? So obviously, this is also going to be the shortest path distance, and this is just going to give you dn minus 1 uv. Okay, is this clear? So the idea is that this k, if it becomes more than n, it just doesn't change anything. Like there are just no more updates that are being done. So it's like saying that if I compute shortest paths between all pairs and then do this update, it's not going to change my value in any way. Right? This is really related to that relax operation. We said when you do the relax operation, you're never going to make a mistake. And once you converge to the shortest paths, you'll just stay at the shortest paths. Okay? Yes?
Why? Because
yeah, good.
Because dn minus 1 uv.
Yeah.
No, never mind. And then you just get weight v is 0.
Yeah? What you're saying is, you could have the weight to itself, but that's just going to be 0, and then you don't get anything. Yeah, good. Okay? So I mean, I can keep computing this recurrence. This is just a formula that I can just keep applying over and over again. But the point is, and okay, so there's one subtlety here. We're assuming the shortest paths exist, that there are no negative weight cycles. But under that assumption, once k hits n minus 1, this is converged, which means if I keep doing the update, nothing changes. So I can afford to basically make k to be like 2n, 3n, doesn't matter. I'm just going to get the same value. Right? There's this notion of convergence. Now this observation is going to be useful for this over here. So now I could change this recurrence. So, okay, ignore what I've written. I'll just rewrite the thing. So here's u to v. And I'm looking at this dk uv. So note that in this picture, I was looking at taking a path of length k and then taking the next step. But instead, what I could do is I could try to find the midpoint of this path, get to the midpoint, and so this would be k over 2 and this would be k over 2. And so what this means is I could basically say dk of uv, the distance, is also the min over all x in v of dk over 2 ux plus dk over 2 xv. Okay? Does this make sense? So I could also use this recurrence. And I claim this recurrence is more efficient. Because to find paths whose length is at most n, the previous step only needs to find paths whose length is at most n over 2. And the previous recurrence from there will go to n over 4, so on and so forth. So instead of going n, n minus 1, n minus 2, n minus 3, which is what your recurrence did over here, or the other way around, you're building it as k goes from 1, 2, 3, 4. Instead, I'm saying, think of k going from 1, 2, 4, 8, so on and so forth. So it doubles each time. So that means that instead of doing n iterations of this k, you only have to do log n iterations. And as we said, it's okay if your k becomes more than n, because you're still going to get the right answer. Okay, so then the way that this is usually described in terms of a table. So let me, just to prevent confusion, I'm going to create this variable L, which I'm going to think of L as log base 2 of k. Okay? So what I'll say is d uv0 is equal to the weight uv. This is my base case. And then I say d uv of L is equal to the min of x over all vertices of d uv L minus 1 plus d uv, d ux dxv L minus 1. This is my recurrence now. It's different from the previous one. Yeah, follow? Maybe you needed extra caffeine to parse through all the notation. Because it's going to get worse with Floyd-Warshall. Or better. Yeah.
You mentioned earlier you could directly save space by removing once you compute k plus 1, you can remove k.
Exactly, yes.
Wouldn't that algorithm just end up being a fancy shortest distance algorithm and loses from my understanding, the whole point of this algorithm is to save all the pairs in the path that is possible. But if you get rid of that data, then that information, then isn't just this a fancy.
So good question. So you're saying that would you then forget the path? So that's a good question. So the thing is, if you really think about all pair shortest path as the problem, if you really wanted to store all the paths, then your storage is going to be more than n squared. Right? Because for every pair, you're going to have to store a path. So in this problem, we only care about the distances. Because
But you're saying your algorithm, you don't disable distance. You can theoretically save this distance once you calculate it in some other theoretical.
you mean store the paths.
Sure.
So in this case, also you're going to get the distance. Even if you don't store all the intermediate stuff, you're getting the distance. The intermediate information is kind of wacky. What it stores is it's storing the shortest path if you could only go k edges. That doesn't seem like particularly useful information to have. Does that make sense?
Okay.
If you wanted to actually store the explicit paths for everything, well, then you're going to have to you're going to need more storage. But in many situations, you're only looking for just all pairs distances. Like this sometimes will come up in routing schemes on a network. So if you have 500 routers, you just compute all pair shortest paths so that every router knows what are the closest routers to it. Because it can then look at everything. Or if it has to send something to some faraway place, it basically knows this information. And often you might not explicitly store the entire path. But does that answer your question? Yeah? Okay. So this recurrence here, it's just a small change. Like if you look at the difference from this recurrence and the next one, here you're actually adding k minus 1 in weight, and there it says you're doing ux l minus 1 xv l minus 1. That one. Okay? And this is effectively what it's doing is it's doubling, because it's using this idea over here. Okay? So note that now L is just going to go up to log n. You just need to do L for all values up to log base 2n. Floor, ceiling, whatever, right? I mean, okay? I'll give you another interpretation for this. Okay, so this is now going to be basically theta n cube log n. So why is it? Because there are a total of n square log n entries, and each entry takes theta of n time to update. Okay? So n cube log n. So this idea of halving is actually related to something else. So I'll ask you a question which is actually pretty tightly connected to this, although it might not look like that. Given a matrix A, okay, how long to compute, I'll say a to the n, or let me call it a to the k, okay? So think of A as some n times n matrix. And forget about fancy things like Strassen or whatever, right? What is the most obvious thing to do? You start with A, you compute A squared, then you compute A cube, A to the fourth, so on and so forth. Right? So you do A squared, A cube, so on and so forth, until you get AK. Right? Now, each of these multiplications is going to cost you how much? N cube. Right? So you do N cube over here, and you'll get theta of n cubed times k. But you're actually wasting a lot of time computing these intermediate powers when all you care about is the kth power. So a better strategy is to do A square, then you can do a square times a square to get a to the fourth, right? This is a square times a square. And you can get a to the eighth by doing a to the fourth times a to the fourth. So on and so forth. Now suppose k is equal to 2 to the L. You just need L iterations over here. And you could do it in theta n cube log k. Right? This is called the trick of repeated squaring. And this is exactly what is happening in that matrix multiplication, in that shortest path idea as well. It's like you're doing some kind of repeated squaring, so that saves you a factor k and it becomes log k. Now you might say, what if k was not a power of 2? You can still make this work. Because once you get all these intermediate things, it's like you look at the binary representation of k and you can piece it together. Like essentially once you have all the powers of 2 less than k, you can multiply them together and you can actually get any k, looking at the binary representation of k. So it's not a bad exercise to figure out. Okay? Does this make sense? So this idea of repeated squaring is really the same thing as what's happening here. And it's actually, there is a way of looking at all pair shortest path as a matrix multiplication computation. So there's a connection between that. Okay, questions? It's clear? Okay. Oh, well, that's fancy. So I actually hit the 100th page. 100 pages of notes. Very good. Okay. And the question now is, can I do even better? And so this is where the Floyd-Warshall algorithm comes in. So let me actually make sure I have my notes in front of me so that I do it correctly. Okay. So the Floyd-Warshall algorithm. So this is actually a very, it's a very strange dynamic program. So obviously we can assume the vertices are labeled from 1 to n. Okay, now I'm going to change the notation a bit. I'm going to call it dr of uv. So what is this? This is the shortest path distance using intermediate vertices of label at most r. Okay, so let me kind of draw a picture for you. So it's kind of saying that, so here's my graph. I'm going to get from u to v using a shortest path. These are all the vertices whose label is at most r, and I'm only allowed to use these vertices. So I can go in here, do something here, and get back out. I'm not allowed to go outside the set. That's what druv means. Okay? So it's different. I'm not having this parameter on the length or the number of vertices, but I have a constraint on the label of those vertices. Okay? Now it should be quite clear that dnuv is really the shortest path distance between u and v. And that's just saying you get to use all the vertices. So this is constraining the vertices that you're using by label. Now what's really funky about this recurrence is with this notion is that you'll see that the recurrence requires a minimization of only 2 terms. So you don't have to actually loop over everything to compute as you start improving your as you update your dynamic programming table. All right. Okay. So, okay, let's now see what is this recurrence. So druv is equal to the min of what? So how are you going to compute druv if you knew what dr minus 1 uv was? values. dr minus 1, r minus 2, all of these values. Yeah?
Distance of u to r.
So you mean d. You have to use this is the recurrence. Yeah, go on.
D of r from,
You don't have d of r.
so it's from d of r minus 1 from u comma r or some x and then actually no.
Okay, so let me draw a picture for you that helps. So here's uv. These are all the things that are less than r minus 1. And let's say this is r. This is the vertex labeled r, right? So what dr minus 1 gives you is the shortest path that goes through here. What you want is the shortest path that potentially also uses this vertex. Because maybe, by using this vertex, there's an even quicker path. So obviously, one option from going from u to v in less than r is to not use r at all. Right? So it's going to be the min of d r minus 1 uv. Right? That's certainly one option. What is the other option? The other option means you're going from u to r and from r to v. Okay? That's the hint. Now, what is the next term? There's just one more term you need to minimize over. So I'm going to actually write this down over here. I'll say case 1, path, I should say, shortest path from u to v with labels at most r does not use r. In that case, I'm just going to get dr minus 1 uv. Case 2 is that the shortest path from u to v with labels at most r does use r. So what this means is that u is going to go to r, is going to go to v. What do you know about all the labels in this path? Yeah?
So like all the labels from u to r, like it can be 1 plus dr minus 1 u r plus 1. Like.
So the labels in this path are all at most r. Right? The path that is going to r, what about those labels? They're also at most r. But you've already used r at the destination. You're not going to use it anywhere in the middle. So it's just going to be r minus 1. Because all the other things over here are going to have label at most r minus 1. It's like saying that if I want to go, using this picture again, this is r. So it's going to do something and go here, and do something and go here. But all of these other things, they're all less than r minus 1. So when the shortest path does use r, then this is just d r minus 1 u r plus d r minus 1 r v. I'm just going to rewrite this over here. So therefore the recurrence then just becomes d r u v is the min of just two terms, dr minus 1 uv and dr minus 1 ur plus dr minus 1 rv. It's very clever. So it says that you can get the next term, like the next matrix in the recurrence, by just doing a minimization of two terms. right? And so R will, of course, go from 1 to n. So there are a total of n cube entries, but each entry only takes a constant time to compute. So you get overall n cube as opposed to any of the other algorithms. It's a very clever dynamic program. Right? I mean, your instinct in shortest paths is to think about, I'm going to take the path and split it in the middle or split it at one end. And so all of those approaches, the recurrence, computing the next entry will take linear time. And here, computing the next entry is just taking constant time. But you have more entries, but again, you can, as we discussed, you don't have to store all of them at all times. Okay? So again, the difference between the basic recurrences and the methods is previously you had 3 parameters. The third parameter was something to do with the length of the path. It was something to do with how many edges are on the path. And here, the third parameter is on the labels of the vertices on the path. Yes? Yeah.
Is the numbering from respect from U to V, or is it just something can be any numbering?
It just doesn't matter, right? You think of when you implement a graph, you just assign labels 1 to n. So this is just saying that you want to go from U to V. It doesn't matter what U and V are, but you only want to use intermediate vertices whose label is at most R. So you can think of it as the intermediate set is going to keep increasing. So initially, when you look at D1 of UV, actually maybe it's worth doing that exercise. Let's look at the base case. Or actually, what is D0 of UV? Which means you don't get to use any intermediate labels. This is just going to be the weight of UV. This is your base case. It's saying don't use any intermediate vertex. But what does D1 of UV mean? So it means that if you want to go from UV, it's considering 2 possibilities. Either you can just take the edge directly, or you can go from U to 1 and from 1 to V. And it's going to take the minimum of these 2 possibilities. And so what is D2 of UV doing? So it says from UV, you can either go from U to V, you can go U1V, you can go U2V, or you can go U1, you could do something like that. Or you could go from U1 to V, depending on the direction. So it's looking at these paths, and so on and so forth. Right? And the nice thing, as I said, is that the recurrence only takes constant time to compute. So as you increase R from 0 to n, every intermediate computation is only constant time. So this is Floyd-Warshall. This is again a theta n cube. And the n cube is because your recurrence looks something like d u v r is equal to min of d u v r minus 1 d u r r minus 1 plus d r v r minus 1. Right? So there are n cube entries. Each of the n cube entries can be computed in O of 1 time. Okay? So this is the Floyd-Warshall algorithm. Okay? Questions? So far, so good? Yeah?
How do we pick these intermediate vertices?
They're just labeled, right? So there's nothing, so think of it as, let's just say you build a graph, you've labeled the vertices 1 to n. you don't have to do anything other than just run this recurrence over, just keep doing this update. So all it's saying, maybe one way to look at this picture, is in the base case, you're just saying, okay, just take one edge. When you do D1, it's saying you are also allowed to go via vertex labeled 1. D2 says you're also allowed to go via any set amongst 1 and 2. D3 of UV says that you can go via 1, 2, or 3, any of them, or in any order, so on and so forth. Now, you're saying, how do you pick 1, 2, 3, 4? I'm just saying it doesn't matter. You pick it any way you want, because in the end, as you finish the recurrence, you're going to go over all possible vertices. When you look at what Dn is, that's saying that take any vertex whose label is at most n, but all vertices have label at most n. So you get to use all the vertices. Yeah? It's a bit, I mean, it's like, there's like a mental switch that he's done over, that they did over there, right? Which is, instead of having the distance be like the third entry in the dynamic programming table, not the distance, but the number of edges, it's actually this label parameter, which is kind of, it's kind of tricky. Okay? Questions? Okay, all right. So there's yet another thing called Johnson's algorithm for all pair shortest path that I thought I would teach, but I think I'll move on. So I think I've said what I wanted to say about shortest paths. There's Bellman-Ford, there's Dijkstra, and there's Floyd-Warshall. These are the three things you need to know, right? And Dijkstra you've probably seen and heard enough before. So Bellman-Ford and Floyd-Warshall. Okay? Questions? All right. So at this point, I think I have primarily taught everything that I want you to sort of know for like a test or an exam or whatever. And so from now on, which is the rest of this lecture, and then how many lectures is there left? 3 more, right? Yeah, 3 more. Okay. So 3 more, I'm going to do more. So there's at least 1 lecture that I want to do where I answer the questions that some of you have posted. And you can also ask me like algorithmic questions in class. I have a feeling it might go on more than 1 lecture because there are enough questions and we can discuss them.